All right. Hello, everyone. This is Miss Allie behind the screen. This is your video lecture for the Registry Review class. We're starting safety this week and regarding the biological aspects of radiation. So we are going to be covering certain topics from the ART registry. Specifically, we're going to be covering section B of your ART content specs 1 through 6. So we're going to talk about units of measurement, radiosensitivity, somatic effects, acute radiation syndrome, a little bit of embryonic and fetal risk, and genetic impact. Okay, so the first section is the units of measurement, and this is really important because the units of measurement are based on your occupational dose. So obviously we use units of measurements when it comes to your dosimeter readings. We also use measurements when it comes to patient dose, so SI units are most definitely going to be on the registry, so it's important to know what these units are, to know the difference between traditional and SI units, because you will see the SI units on the registry, on the HESI exam. Sometimes they'll utilize a traditional unit such as RADs instead of grays. So it is important to understand, and they may use REM instead of Sieverts. So I want to make sure you guys understand the difference of those. So first off, we're just going to go back and kind of review the radiation quantities and their units of measure so that you guys can understand the difference. So I'm going to start off by showing this chart. My main reference for these slides are going to be from your SHARE radiation protection textbook that you guys had in module 5 when you went over radiation protection. So first off, I'm going to get my little laser pointer here and my arrows. So what I really want you to pay attention to is the type of radiation and the quantity, because in order to understand the SI units, you have to kind of know what they're actually measuring. And I'll give you a couple examples so that you understand that moving forward. So the first example they give you is the type of radiation. So obviously in our field, we deal with X-rays. They use gamma radiation because in terms of the weighting factor and how radiation is measured, X radiation and gamma radiation is very, very similar. So they typically can combine those together because they both have a weighting factor of 1, and we'll get back to that in a few slides. So whenever we're talking about exposure, meaning that when you take an X-ray exposure, you have to think about the X-ray photons starting in the X-ray tube and transferring to your image receptor. And that's when you use the term exposure. We use that in imaging technique, and it refers to a measurement of radiation in the air. So this is before the radiation hits the patient. It's before it's collected by anything, including the IR. So whenever you're dealing with exposure, the SI unit of measurement is going to be coulombs per kilogram, or C/kg. Now, this is important because it is different from grays and Sieverts, and I'll tell you why in just a minute here. But the way that I kind of think about SI units are when you think about measuring. So for example, if we pull a tape measure, you obviously have inches or centimeters. Inches is going to be our standard way to measure, and centimeters is going to be more of an international unit. So the international units, or the SI units, are what we're going to focus on. So coulombs per kilogram is what you need to know. So you may have heard the term Rankine. Rankine would be more of a traditional unit, measuring X-ray exposure in the air. Well, when we're focusing on SI units, just note that on your ART exam, they're only going to use the SI units. Now, they may want you to convert from traditional to SI, but mostly they're going to stick with SI units. So it would be the same as if you were converting inches to centimeters. Instead, what we're doing is converting Rankines to coulombs per kilogram. That would be a comparable exchange. So it is important to note that your quantity is exposure and you're measuring in the air, okay? So they wouldn't refer to grays measuring in the air. Grays are going to be inclusive when you're talking about absorbed dose, okay? Or if you are measuring in the air and they're trying to measure air kerma, you're always going to see little abbreviations down here, and we'll talk about that again as well. So anytime you're dealing with grays, which is an SI unit, the traditional unit would be the rad. Grays are most likely you're going to see either air kerma or absorbed dose. Absorbed dose is the major way that we use the SI unit grays. And you're going to see here that if we're measuring in the air, you're going to notice that there is a little abbreviation of GYA. A stands for air. When we're measuring absorbed dose, so this would be the dose that is absorbed inside, you know, for example, for a patient, you're going to see the abbreviations GYT or gray T. T is going to stand for tissue, which makes sense because when we are talking about our patients, there's going to be absorbed dose in the tissue of the body. Okay, so if we're not measuring in the air, so if we're not measuring the exposure, we're actually measuring the amount of dose inside of an object or a patient, that's when we move to grays. And if it's a gray and you see the abbreviation T, that stands for tissue. If they're trying to measure air kerma or they want to see a certain amount of radiation in the air used in a different fashion, then they'll use gray A, which stands for air, okay? Most of the time, you know, they'll just if they're just using gray GY and you don't see any abbreviation, it's going to be referring to absorbed dose. All right. So the radiation effect measured is the amount of energy per unit mass. This also has to deal with LET. We'll get to that in some future slides also. So the last thing I want to mention are Sieverts. This is really important. This is going to deal with occupational dose, so and in our patient dose when there's multiple types of radiation involved. Specifically, we're going to talk about equivalent dose and effective dose. They are a bit different. Equivalent dose means that you have different types of radiations involved. For example, if you're measuring if an object or a patient was exposed to X-rays and gamma rays, you're going to have measurements of both of those together. So that's going to be an equivalent dose when there's multiple types of radiation. And instead of using gray, you're going to convert that to Sieverts, okay? And the reason why is because gray only refers to one type of radiation, whereas Sieverts can include multiple types of radiation, okay? So it's just a different way of measuring radiation to body tissue. Of course, we also have effective dose. Now, it's very similar to equivalent dose, but on effective dose, it doesn't necessarily mean that you have different types of radiation. It can, but what it also means is when you have some kind of radiation exposure to the patient, it means that there's different tissues involved. For example, your gonadal tissue versus your nerve tissue. Those types of tissues are going to absorb radiation differently. So therefore, you're going to have to convert from grays to Sieverts because each of those types of tissues have different radiation weighting factors, meaning that some tissues are more affected by radiation, some are more radiosensitive, some are radioresistant, so they're not going to react the same. So therefore, an effective dose is going to compare different types of tissues and different weighting factors that would result in biologic effects. Okay, so this is just kind of an overview. It's very important to understand the SI units as compared to the traditional. Remember the traditional, I talked about rads, are rads or Rankins when it comes in coulombs per kilogram, rads to grays, and then rems to Sieverts. Those are going to be the comparison. So we'll come back to that in a little while. So just to go over absorbed dose in a little bit more detail, again, remember absorbed dose is going to be absorbed dose is going to use the SI unit of gray or gray T, so for tissue. So it is the quantity of energy of mass absorbed by a radiated object. So it's not the amount of radiation in the air anymore. Once that radiation or exposure, once that radiation hits and is absorbed by the tissue, it's going to be now absorbed dose. This is where there can be biologic damage. You guys obviously have heard of, large doses of radiation causing skin burns or cancer long term or cataracts. Those are all going to be different examples of biologic damage resulting from exposure to radiation and being absorbed by certain tissues. We use shielding. I mean, that's a prime example to safeguard over certain tissues that are more sensitive to radiation, so to protect them. So again, different tissues are going to react to radiation differently depending if they're radiosensitive or radioresistant. Okay, and of course some structures are going to absorb more energy than radiant energy than others. It just depends. Bone, for example, usually that's going to be able to absorb more x-rays because bone is more dense. Whereas other structures like your chest or your lungs, x-rays are more likely to transmit through your lungs because they're less dense. Okay, so you guys have heard about the atomic Z number, or the Z number, the atomic Z number. Absorbed dose, again, is going to depend on the atomic number of the tissue. Again, comparing bone to soft tissue, for example, the mass density of the tissue, the energy of the photon. If you have a higher energy photon, it's going to be able to transmit through even higher atomic number tissues. So just remember, this is an important slide here. The SI unit of absorbed dose is gray. More specifically, you might see a little T down here, and that's going to stand for tissue. And it's the most common. If you just see gray without a small abbreviation for T or A, then just assume it's absorbed dose, okay? So just as a reminder, just like I spoke with the example of inches to centimeters or centimeters to inches, gray is the SI unit, rad is going to be the traditional unit. And you do want to know the conversions because, again, your HESI might mention rad and your ART exam might mention gray. It doesn't mean you have to memorize two different types of units. You just have to know the conversion. So it's like knowing how many centimeters are in an inch. So I will prepare to teach you again if you don't remember. I'll give you a little trick that helps me. I hope it helps you as well. So you can see from this slide here that the number of rads divided by 100 equals the number of gray. Okay, so for example, if you have 5,000 rads, you just divide that by 100 to give you the amount of grays. So 5,000 divided by 100 would be 50 grays. Okay. Example 2, if you have 5 rads, you want to divide that by 100 again, which would be equivalent to 0.05 grays. Yes, that if you're not a math person, that could seem very confusing and it's hard to remember sometimes. So here's my quick example to help you remember. I like to just think of little tricks and tips, and I'm sure you guys have done that yourself. When it goes from rads to grays, I use the initials of the first letters. So rads, I think of red pennies. So there are 100 red pennies in one green dollar. Okay, so there are 100 red pennies in one green dollar. So the rads I think of as a penny or 1 cent, and grays I think of as $1, and that's a 1 to 100 ratio. So if you can remember that your rads are your pennies and your grays are your dollars, then you're going to be able to use that conversion quite easily. So again, if I had 5,000 rads, I think that I have 5,000 pennies. So if I want to convert that to dollars, I know that 5,000 pennies is the same as $50, or the same as 50 green dollars. So red pennies, green dollars, that's how I remember it. I hope that helps you. Okay, so let's move on. So again, this is another chart that comes from your Share textbook to just kind of help you out if you do need to know the conversions. It's possible you may need to on the registry. I've heard rumors that there's not a lot of math but I don't know if converting from one unit to another is math, or really a math problem, or if it's just more, you just have to know the conversion, but it's always good to know just in case. So the ones that I want to focus on, again, I don't think you need to really know these real long, more physics-based equations. I want you to focus down here on these two right here. This is what we use the most. Again, these two are more of the physics-based. I don't think you have to know that, but just note that 1 gray, again, is the same as 100 rads. Centigrade, okay, is the same. Centigrade is going to be the same as a rad. So centi meaning 100. So if you see the little c, that means that you divide the gray by 100 to give you the amount of centigrays. And of course, the little m is going to be your milligrays. So, you know, basic conversions, you may need to know how to convert milligrays to grays or centigrays to grays. So if you need help with that, you know, feel free to reach out to me now, and I can give you some practice problems. I also want you to pay attention to Sieverts. That's the other SI unit that we were talking about. And remember, I said the traditional unit is the rem, okay? So again, I want you to think of rem as red pennies, and I want you to think of Sieverts, and I want you to look at that S, and I want you to think of the dollar sign, okay? So again, there are 100 red pennies in $1 or dollar sign. So there's 100 rem and 1 Sievert, okay? It's the exact same conversions from rads to grays. So there's 100 rads and 1 gray, and there's 100 rem and 1 Sieverts. They are the same conversion. This just is absorbed dose, and these are demonstrating equivalent and effective dose, but it is the exact same conversion, okay? These, again, I don't think you need to know for your registry, so it's great to have the information, but I'm not going to focus on that. All right, so let's go back to equivalent dose, because we talked about that in my introduction. So the definition of equivalent dose is the product of the average absorbed dose. Remember, absorbed dose by itself is just grays. But if we're focusing on different types of energy or different types of radiation, then it's going to be different. It's not just going to be grays and absorbed dose. It's going to be an equivalent dose because you're adding multiple types of radiation. So again, equivalent dose is the product of the average absorbed dose in a tissue or organ in the human body, and it's associated, this stands for weighting factor, chosen for the type and energy of radiation in question. So it's the amount of energy absorbed by the body when you're considering different types of radiation. What I mean by that is there could be X-rays, gamma rays, neutrons, alpha particles. Those are all different types of radiation, and they all have different energies. So in order to get an equivalent dose, you have to consider that maybe, you know, the tissue's absorbing X-rays and gamma rays, for example. And we do use gamma rays in medical imaging. I believe in nuclear medicine, I think, using gamma cameras. So, you know, this is important in our healthcare field, so it is important to know what equivalent dose is. It is used for radiation protection purposes when a person receives exposure from various types of ionizing radiation. Again, if they're doing a nuclear medicine scan and then they have a foot x-ray afterwards, in those two different types of exams, they've received different types of radiation. So instead of having an absorbed dose, like if the patient's like, well, how much dose did I receive? You would not give them their dose in grays, because they received radiation from gamma, and they received radiation from, you know, normal x-rays. So instead, we would give them an equivalent dose, and it would be in the radiation unit Sieverts, okay? Again, it measures biologic effects, and it's expressed in Sieverts, or in a subunit of Sievert, like a millisievert. So grays deal with only absorbed dose of one type of radiation. Sieverts consider multiple types of radiation, okay? The Sievert replaces the rem. Again, the rem is going to be the traditional unit. It's a smaller unit. Remember, red pennies. So 100 rem are going to equal one Sievert, or $1 sign, right? So 100 rem and 1 Sievert. All right, so you may have to know the equation for equivalent dose, and really, it's all it is if they have a dose of radiation, whatever that number is, you times that by the radiation weighting factor. And what is the radiation weighting factor? Well, each type of radiation can have different effects on the body. So X-rays are relatively low weighting factors because they're not super harmful unless you have extreme doses. But you'll notice that they have a weighting factor of 1, which is the lowest. But if you have alpha particles, which is like a nuclear bomb, that radiation weighting factor is going to be 20 because it's a lot more damaging to the body. So it's going to have a higher weighting factor. So great. So you can actually check my facts. You can see here again that, like I said, they call it a quality factor. So just note again that let me kind of write that out. So let's see here. So quality factor also can be known as the WR, or the radiation weighting factor, or weighting radiation factor. Weighting, not like you're waiting in a pool or you're waiting to be seen. It's the weight, like you're lifting something. Weighting factor, as in, it has a higher weight. So the quality factor of X-rays, I would know this. You should know that they have a weighting factor of 1. And gamma photons too. So when you're using the gamma factor or gamma radiation, it's going to be around the same as X-rays. They're very, very similar. The only difference is the source of where they come from. Beta particles also, in some types of medical imaging exams, or even natural radiation, beta particles exist. All of these three kind of have the same effects, or biologic effects on the body. So they're going to have a radiation weighting factor of 1. Now you're going to notice, and protons as well, these ones down here. These aren't as common though. What I do want you to notice is that neutrons, these thermal neutrons or slow neutrons, they're going to be a little bit more damaging to the body. So they'll have a radiation weighting factor of 5. Fast neutrons are going to have a radiation weighting factor of 20. I'm not going to go into the physics of why all of these particles are higher weighting factors. I would maybe just note that they are more damaging, and that's why they have a higher weighting factor. Again, you're going to see alpha particles. All of this is probably involved in like nuclear energy. So nuclear power plants, we've all seen and heard about, nuclear accidents that have happened, and Hiroshima, and all of those that we learned in radiation protection class, that those types of radiation are a lot more damaging than X-ray is. So they have a higher weighting factor, and you can see that here, quality factor. So it is good to know these numbers. They're not too hard to memorize if you actually just think about what type of radiation they are. Alpha particles, nuclear energy. X-rays, what we practice, and we take X-rays every day. Gamma, again, and things to that nature, to where in medical imaging typically we use the lower energies. But anytime there's multiple types of radiations involved, again, you no longer have an absorbed dose, you have an equivalent dose. So you're not going to give their dose in grays, you're going to give their dose in Sieverts. Okay, and that's why that does that. So equal absorbed doses of different types of radiation produce different amounts of biologic damage, thus resulting in Sieverts. And then the concepts of dose equivalence takes the biologic impact into consideration by using or modifying the quality factor, again, weighting radiation factor, to adjust the absorbed dose value. So I can maybe do a little example here, if I can. Let me see if my pen works. Oh, it used to work. Maybe it needs to be. Unfortunately, it's not working today. Okay, I can manually draw it. It might be a little messy. Let's see. All right, let's give it a try. So again, remember that equivalent dose is the, let Let me try to go back once, guys, because there actually is an example on the next slide, but I want to give you a prelude to the example. So remember, equivalent dose is the dose, right, or D, times WR. All right, so that's going to be in Sieverts. So for example, let's say that there is a patient that has 5 gray, which is super huge. That would never be realistic, but this is just an example. 5 gray of X-ray radiation dose and 5 gray of gamma radiation. Okay. What is their equivalent dose? Well, all you're going to do is you're going to take the amount of radiation in grays and times it by the radiation weighting factor. So 5 grays times 1 is going to be the equivalent of 5 sieverts of radiation of X-rays plus 5 grays of gamma. So you again times that times its weighting factor, which again in this case is 1. So you're going to have 5 sieverts of gamma. So our total radiation is going to be 10 sieverts of equivalent dose. Okay, so you can see here that in the equation it started off in grays because you have 5 gray of one type of radiation, 5 gray of another, but because we're using different types of radiation, we have to change that conversion value measurement to sieverts. So your answer will always be in sieverts, and I'm going to show you a book example in just a minute here. Okay, make sure, let me go back to my laser pointer. And it looks like I just turned on the transcription, and I don't know how I did that. So we'll just keep moving on, and now you get the transcribed version if you don't understand what I say. Hopefully it works out pretty good. Okay, so this is the example of equivalent dose using grays and sieverts. You can see that here. And we're going to go through the example together. And this one's a little bit more difficult, but still workable. So you can see here that an individual receives the following absorbed doses. So you can see that they're all in grays, right? But this individual received different types of radiation. So now that's why it changes to an equivalent dose. So you can see that they have 0.1 gray of radiation. So they mark that down here. And then again, the radiation weighting factor of X-rays is 1. So they're timesing that together. They had 0.05 grays of fast neutrons. Well, if we refer back to our chart, we know that fast neutrons have a weighting factor of 20. So you're going to multiply 0.5 times 20, and that gives us 1 sievert. It goes from grays to sievert. And it says they had 0.2 gray. Remember that little T stands for tissue. 0.2 gray sieverts of alpha particles. So again, alpha particles have a weighting factor of 20, so they had to times 0.2 by times 20. What is the total equivalent dose? Well, they kind of worked it out for you. So they times each of those absorbed doses by the weighting factor, which is over here. And then to find the equivalent dose, the total, all you do is you add those equivalent doses together. So 0.1 plus 1 plus 4 gives us our total equivalent dose of 5.1 sieverts. Okay, so that is equivalent dose using different types of radiation that has different weighting factors. All right, I think this is a same example. So again, let's say a person receives 5 grays of X-ray photons and 1 gray of gamma photons. All right. So first things first, you notice these are gray. So refer to the quality factor of the radiation weighting factor. So X-ray photons are 1. So we have 5 times 1, which is 5. And then 1 gray of gamma photons. 1 is the weighting factor. So 1 times 1 is 1. So what is the equivalent dose? Well, 5 plus 1 is, oops, sorry, I went too far. So 5 plus 1, it doesn't give us the answer, is 1. So again, I think this slide was made for me to work that problem out with you. So I think I just got ahead of myself a little bit. So let's go back and work that out. So again, if we have 5 grays of X-rays, we're going to multiply that by the weighting factor, which is 1, and that'll give us 5. And if we have 1 gray, sorry, that's supposed to be a 1. If we have 1 gray of gamma, we're going to multiply that by the weighting factor, which is 1. So 1 times 1 is 1. Our total equivalent dose is 5 plus 1, and that will give us 6. Is it 6 grays? No. Remember, equivalent dose is always in sieverts, so our answer is going to be 6 sieverts. Okay, I hope that makes sense. All right, so again, you know, equivalent dose uses radiation weighting factors when you have multiple types of radiation. Remember that effective dose utilizes tissue weighting factors. So when you have radiation to different parts of the body, like I said, they're going to react to radiation differently. Gonads are going to be much more radiosensitive, so their radiation weighting factor is going to be higher. So effective dose refers to different tissues, all right? That's basically what this is saying without me like going through all of it. So I will read it though. So effective dose uses tissue weighting factors to adjust the quantity equivalent dose to reflect the difference in harm to the person as a whole, depending on the tissues and organs that have been radiated. Therefore, effective dose takes into account both the types of radiation and the part of the body irradiated, and that's important. So you can see here that if you pay attention to the equation, remember, just again as a reminder, let me pull this here real quick. Just a reminder that equivalent dose is your dose multiplied by your radiation weighting factor, which is here. Well, for effective dose, now they're adding radiation weighting factor and this other factor, which is tissue weighting factor. Okay, so now we're timesing tissue weighting factors for that as well. So in the example they give, I believe this is from your shared text or Bouchon, I can't quite remember, but it says the weighting factor for alpha particles is 20, which we knew that, and the weighting tissue factor for lung is 0.12. So if the lungs receive an absorbed dose of 0.5 gray from exposure of alpha radiation, what's the effective dose in sieverts? Well, of course, we're going to take the initial dose, so that's 0.5 gray, and we're going to multiply it by the alpha particles. We know alpha has a radiation weighting factor of 20, so we're going to take 0.5 gray times 20, and then we know that primarily the lungs are receiving the dose. So we have to figure out the lung weighting factor, which they gave to us, which is 0.12. So we're just going to take that multiplied by the alpha radiation weighting factor times the amount of radiation, which was 0.5 grays, T, which is tissue. So of course we know that when we have different types of radiation or we have different tissues, we're no longer going to use gray, we're going to convert that to sieverts. So if you take 0.5 times 20 times 0.12, it's going to give you a total of 1.2 sieverts, and that is the correct answer for this particular problem. Okay, so grays and sieverts essentially are the same thing. So 1 gray, this is important, let me write this down so that you want to put this in your notes. 1 gray, let me see here, one sec. 1 gray essentially is equivalent to 1 sievert. But just remember, gray is absorbed dose and sievert refers to effective and equivalent dose, okay? All right, moving on. This is an example. I do not think you will have to memorize these weighting factors, but I would not hold me to everything I say. I just want you to pay attention to look at the different tissues in the body and look at the weighting factor and how they compare. We know that we always should shield gonads, so of course that's going to have your highest weighting factor of 0.2. Red bone marrow is another radiosensitive organ or radiosensitive tissue. So that's going to have a 0.12. Your colon is radiosensitive. Your lungs are pretty radiosensitive. Your stomach, so those are going to have a 0.12 radiation weighting factor. And then you can see as we go down the list, your other areas of the body are a little bit more radioresistant, so their radiation weighting factor is smaller. You can see that skin and bones, of course, are the most radioresistant. That's why we don't put lead shielding all over our skin. And when we do wear lead, we still have our arms out and our legs out, so that's because bones are really radioresistant too. And then this remainder, they just do an average of 0.05 for the rest of the tissues in the body. So just to give you some insight on that. Going back, remember we talked about exposure. So that's those coulombs per kilogram. When you're measuring exposure of radiation in the air, you're going to use coulombs per kilogram. The definition of exposure is the total electrical charge of the sign, either all pluses or minuses per unit mass, the X-ray and gamma ray photons with energies up to 3 million electron volts generated in dry air, standard temperature. I don't think you're going to need to know all that. What I want you to know is exposure measures air. And the measuring tool that you need to know for that is coulombs per kilogram. That's the SI unit. The Rankins would be the traditional unit of measuring exposure in the air. So please just kind of focus in on exposure, air, coulombs per kilogram, SI unit. Okay? So, yeah, this is just a long definition. I don't think that's super important. Again, coulombs per kilogram, that's the basic unit of electrical charge. So think about exposure, X-ray photons, you have to have an electrical charge. When the photons leave the X-ray tube, there is charge. So coulombs per kilogram, again, is going to be your unit. It does represent electrical charge flowing past a point in a circuit in 1 second when an electric current of 1 ampere is used. Well, that sounds familiar. Ampere or amps or milliamperage per second mass, we actually utilize that. So it makes sense that coulombs per kilogram is measuring our exposure. We know that ampere is the SI unit of electrical current. Mass is the most common example. We use that all the time. So we use, milliamps per second. Again, this is the SI unit for exposure. And it is equal to an electrical charge of 1 coulomb produced in a kilogram of dry air by ionizing radiation. So coulombs per kilogram, measure exposure in the air, and amperes or milliamps, mass is the unit for electrical current. These are the, again, I'm not going to go through these, but these are more charts. They're everywhere in your textbook, so make sure you just know the difference between traditional and SI equivalents. Again, 100 red pennies equals 1 green dollar, and 100 red pennies equals $1 sign, to help you kind of remember that. Equivalent doses are in Sieverts, absorbed doses are in grays, exposure in the air is in coulombs per kilogram. You can see this big R here stands for Rankine, and that's the traditional unit. All right. Okay, air kerma, this is kind of something that, you have exposure in the air, you have gray tissue. So what is air kerma? So air kerma is the SI quantity that's used to express radiation concentration transferred to a point, which may be on the surface of a patient's or radiographer's body. So think about, it's not really absorbed dose yet because it's located on the surface. So if you're measuring entrance skin dose, for example, you're technically not measuring absorbed dose because you're measuring the radiation right at the surface of the body. So it's going to be actually an air kerma measurement. So it's still going to be gray T or gray A, but it's really focused on the surface of the body, and that's why it's a little bit different, okay? So it still denotes a calculation of radiation intensity in air, but instead of, just in the air, it's going to be most on the surface of a body of the patient that you're imaging. Okay, so if you're ever wondering what it stands for, KERMA actually is an acronym. It stands for kinetic energy released in matter. And I've also heard it kinetic energy released in material or kinetic energy released per unit mass. They're all kind of used interchangeably there. Okay, so It's typically, again, if it's used in the air and it's not referring to the surface, it's going to be used, it'll have metric units of joules per kilogram, but it could be stated in gray. When gray is used, it indicates the kinetic radiation energy deposited and absorbed in a mass by air, typically on the surface, or GYA, that's what that little A is for. When it's absorbed in a massive tissue, then it's going to be used as gray YT. So if it's absorbed at the surface of the body, you might see it utilized with a little T instead of an A. Dose area product, this is on your ART content specs, so I would review this, make sure you know the definition. It is the sum of total air kerma, or the total, that total exposure at the surface, exposed area of the patient's surface, or a measure of the amount of radiant energy that's been thrust into a portion of the patient's body. So it's a large area that you're adding together. It's a sum of the air kerma over a portion of the surface of the body, or some kind of place that received a large amount of radiation. So they measure that in dose area to product. And you can see that it's measured typically in milligrays per centimeter square, because you have a larger surface that you're measuring. You're not just measuring one little point. Okay, so again, it determines the entire amount of energy delivered to the patient by an X-ray beam. And it is used in radiography and fluoro, so you should review dose area product. I could see that popping up on your HESI in your registry exam for sure. All right, let's talk about dose-response relationships. It's been a while, right? But we utilize these dose-response relationships to represent examples of the effects of radiation on short-term and long-term exposures, and then also on the biologic effects of radiations, depending on dose ranges and whether there's a threshold or not regarding to the effects of radiation. So they're demonstrated graphically through a line or a curve, and they describe the type and degree of radiation damage. So there are 4 types. I'm sure you guys remember: linear, nonlinear, threshold, and non-threshold. So I'm going to go over those for you. And I'm going to give you all these fancy tricks so I can get to the next slide. All right, so the first one is extremely important, probably the most common type of dose-response curve that you will see, and it is the linear non-threshold. So to put this simply, it is a linear response curve because the line that is represented in terms of dose and response is a straight line, so it is linear. When we talk about non-threshold, I want you to think about doses. So if there is a non-threshold response, it means that any type of or any amount of radiation essentially could cause a biologic response or be harmful to the body, for example. So because any amount of radiation is harmful, you're going to see that straight line start at 0, because as the doses increase, remember, it's going to increase the response or the amount of biologic effect. So in this example, you're going to see as we increase our dose of radiation, so this would be an equivalent dose, let's call this 2, we'll say this 2 Sieverts, you're going to see that there's an increased dose of a response. Remember, this is our response line. So the y-axis is going to be your response, the x-axis is going to be your dose. And you're going to see there's a direct effect. So as radiation goes up, the potential amount of harm to the body or to the tissue also goes up. That is linear non-threshold. It is a direct effect, and it means that any amount of radiation can be harmful to the body. So the response is directly proportional to the dose in this example. So basically, if the dose is doubled, the response is doubled. So if we have 4 Sieverts of radiation, you can see that the dose is, it is directly equivalent. And so from 2 to 4, this doubled as this doubled here. So types of effects that follow this curve are cancer and genetic effects. So if, and these are also considered long-term effects for that matter. So as the amount of radiation goes up, you are increasing your chances or your risk of cancer. As radiation dose goes up, long term, you are increasing your risk of genetic effects as well. We also utilize this curve to follow a LARA because we assume that any amount of radiation could be harmful to our patients, and that's why we shield them. That's why we collimate. That's why we have exposure index numbers to make sure we're not overexposing the patients. So this curve is our representative curve for a LARA also. All right, so nonlinear, non-threshold. Again, as it's when we're talking about non-threshold, it means that any amount of radiation potentially could cause an effect, but when you see it's nonlinear, you're going to, and I'll use this one as an example, you're going to see here that as the dose increases, in this example, yes, your risk or your biological effect is going to go up, but it's not going to go up a lot. So basically in this example, it's saying, you know, yes, I'm increasing the radiation dose, but the amount of harm that could happen is not really going to increase significantly until the dose is at a certain level. But it still does show that as dose increases, the biological response, the biologic response could increase. Consequently, this one, as the dose increases, you're going to see a real jump in the response, meaning there could be a lot of harm to the body. But as the dose gets to a certain amount, it's going to start kind of trailing off. Varied doses produce varied responses in these examples, and responses will increase rapidly or taper off as dose increases. So that gives both examples there. We don't really have a lot of things that represent these. These are just good examples for you. Now this one is very interesting, and this is important because we have had acute radiation syndrome is really going to be an example of the sigmoid response curve here. So this is going to be your threshold curve, and it's going to be nonlinear. More specifically, because it looks like an S, you can kind of see that S shape, that's going to represent a sigmoid curve. So you might hear that sigmoid terminology. So you're going to see here that the dose has to be a certain amount. So for example, if I drew some imaginary lines that represented sieverts of dose, so for example, if each line represented 1 sievert, you're going to see here that it would take almost 3 sieverts before we even have some kind of response. So this sigmoid threshold nonlinear curve is telling us that, yeah, radiation is okay. Up to 3 sieverts is going to be fine. You're not going to have any harm. There's not going to be any biologic effect. So because of that, you know, that this is representing a threshold to where it's stating that any radiation under this amount of dose is going to not be harmful or has the potential of not harming your patient or tissue or whatever. But you know, so a good example of this would be like high doses of radiation, like a nuclear bomb is a crazy example, but it is an example. So if we had a really high dose, like 3 sieverts of whole body radiation from a nuclear explosion, you're definitely going to see immediate responses, skin burns, which is erythema, desquamation. You're going to see GI effects. You're going to, you know, have vomiting, nausea, hair loss, anything that is so extreme because you have such a high dose of radiation, it's going to cause an immediate effect on that. So again, the threshold means it's going to take a certain dose before a response will manifest. Again, yeah, acute radiation syndrome is a big one. I know you guys learned about that. We'll cover it a little bit more in today's lecture. So again, the whole body dose must be greater than 1 sievert for this type of effect to occur. Again, I use these little lines to represent 1 sievert each. So 1, 2, 3. So in this example, you're not going to have for example, I'll use erythema or skin reddening as the example. So you're not going to have that erythema manifest until you've hit an exposure of 3 Sieverts, which is extremely high, and could most definitely, kill a person if they were exposed to that amount of radiation. Radiation therapy is another good example of high dose radiation, to where I'm sure you guys have seen pictures that sometimes patients are, they use radiation therapy to help kill tumors or cancer cells, but the area around the cancer, the skin around it, the patients have received skin burns. It can damage the skin. They can have hair loss because of the radiation therapy. Yeah, all of those are going to be greater than 1 Sievert. So this sigmoid curve is really important, and it does represent high doses of radiation. And in medical imaging, radiation therapy is a great example. All right, so going back to the non-threshold linear, again, this type of dose response curve is a non-threshold, so it means that any dose has the potential to cause a response. Diagnostic x-rays, ALARA, we follow this dose response curve because we tell our patients we need to shield you because we don't want, radiation to harm you. In realistic terms, diagnostic x-rays is relatively low radiation. CT is a lot higher, radiation therapy is a lot higher, but diagnostic x-rays, there's been a lot of talk that, we shouldn't even shield anymore because diagnostic x-ray radiation is so small, so our patients, are not going to be harmed. But as long as we follow this dose response curve and we follow ALARA, we're going to assume that any amount of radiation can be harmful, okay? So again, non-threshold radiation, regardless of the size of the dose, it is expected to produce a response or the ability to cause harm, is what I say, because it helps me remember it. So that's where we get our dose limits. You guys have learned about, annual occupational dose limits, annual dose limits that patients can have in medical imaging. So dose limits, we base those off of this non-threshold linear dose response theory. Also, radiation-induced genetic damage and late effects follow that linear non-threshold curve. That's what I said. Genetic effects in cancer are going to be the non-threshold linear. Yeah, so that's pretty good for that slide. All right, so let's talk about radiosensitivity. So we talked about before, some tissues and cells are going to be more sensitive than others. So it is important to know which ones are highly radiosensitive and which ones are more resistant, so you can focus in on that when you're taking your x-rays. So of course, physical and biological factors affect radiosensitivity, including cell maturity, proliferation, which is the division rate of the cells. So of course, think about just being young and active. So your young cells, they have the ability to divide more. So of course they're going to be more radiosensitive. They're young, they're ready to divide, they're active. So they're going to be more radiosensitive. So, we want to protect your young cells. Also, the fetus, of course, is more sensitive than a child would be. So that's why we always protect our pregnant patients, and of course our pregnant occupational workers, because the fetus is sensitive, most sensitive in the first trimester as the fetus grows, and as you get closer to the third trimester and right before you're ready to deliver, the baby becomes more radiosensitive at that point. So first trimester is really important. That kind of describes the law of Burgundy and Trimpeneau. Don't let that law make you freak out. Just note that it's really just saying that some cells are more radiosensitive than others. So it's saying that the radiosensitivity of the cell is directly proportional to the reproductive activity and inversely proportional to the degree of differentiation. So what that means is if your stem cells, your cells used in reproduction, those are going to be very radiosensitive, and your young cells that divide are going to be radiosensitive, so they're going to need to be protected as well. So cells most active in reproducing themselves and cells not fully mature are the most harmed by radiation. You got to think of like your mature cells, your brain cells, your nerve cells. Those are all mature. So when we do fluoro, we don't protect our head, right? We don't wear this full lead, helmet, because our brain, our nerve cells, and our brain cells are very, very mature. So they're more radio resistant. They're not going to be harmed from radiation. But we do protect our abdomen. We protect our gonadal region because obviously those cells are more radiation sensitive. So the more mature and specialized the cell, the less sensitive it is to radiation. So that's all the law of Burgundy and Trimpeneau is saying. Make sure you know the difference between radiation, or radiosensitive cells, and radioresistant cells. Okay, so stem cells are radiosensitive, mature cells are radioresistant. Make sure you remember that. Young tissue is radiosensitive, older tissue is radioresistant. Your skin tissue, you have your skin your whole life, so it's definitely more radioresistant as you get older. Another thing is metabolic rate. So high metabolic rate is going to be radiosensitive, low metabolic rate is going to be radioresistant. Again, increased proliferation or division of cells and growth rate is going to cause more radiosensitive cells. So that is all describing the law of Burgundy and Trimpeneau. All right, so according to this law, we have to know which cells are the most sensitive because those are what need to be protected. So again, immature cells, undifferentiated cells, such as stem cells, rapidly dividing cells, reproductive, are going to be the most radiosensitive, okay? Make sure you know these three because that'll help you with the law of B and T. All right. Again, if they have a high cells, so I'm repeating myself, I guess, because this is important. But again, the law of B and T says that cells that have a high division rate are more radiosensitive. Cells that have a high metabolic rate are more radiosensitive. If they're not specialized, again, think of your brain cells. They're highly specialized. Non-specialized are going to be very young cells. So they're going to be radiosensitive. And then cells that are well nourished. So oxygenated cells are going to be more radiosensitive too. So something to think about. I like this little chart. This is from Bouchon, I believe. It gives you least sensitive cells to the most sensitive cells, with bone marrow and lymphocytes being the most sensitive cells in the body. Please know this. I feel like maybe this will pop up on your HESI or Registry. Of course, I don't know, but HESI I may have heard. You should know the most sensitive cells, so review these. You can see that your liver, nerve cells, pituitary, thyroid, mature red blood cell, those are all going to be least sensitive. Your skin's kind of in the middle. And then your eyes, your gonads, bone marrow, and lymphocytes are the most sensitive. Here's some examples of radioresistant cells. Of course, bone, liver, kidney, cartilage, muscle, nervous tissue, all radiosensitive. Blood cells, again, lymphocytes, by far most radiosensitive cells in the body. Stem cells in the bone marrow are really radiosensitive. These numbers are dose limits from the NCRP, so I'm sorry, not a dose limit, but very important to probably know. So a whole body dose of 0.25 gray could depress blood count and cause your body to get really sick. So I'm not sure if these numbers pop up on the registry, but it's good to just kind of practice just in case. Epithelial tissue does divide rapidly, so it will be highly radiosensitive. And remember, if you're not sure what epithelial tissue is, it's the tissue that lines like your stomach and your liver. It's the tissue that lines that. So of course it's trying to protect, your organs. So it is definitely radiosensitive. And that's why we shield abdomens, Muscles, of course, think of your biceps, your quads. We don't wear lead all the time when we take x-rays as technologists. So, these are going to be relatively insensitive and, more specialized. So, and they have fewer cell divisions. So it's going to be radio resistant. Nerve tissue, again, highly specialized. It's going to cause really high doses to cause damage. So if we ever were exposed to like a nuclear, nuclear explosion or something, you're going to keep your brain, your mind's going to stay, but your body's going to deteriorate before that, because you have so many other tissues in the body that are more radiosensitive than your nerves. So, again, they're very specialized. No cell division, so they're going to be insensitive to radiation. Of course, reproductive cells we shield. So we know that they include immature sperm cells and, of course, your ovaries. They're extremely radiosensitive. They divide rapidly. They're unspecialized. And they require 10 rads or 0.1 gray or more to increase the chances of mutation and genetic effects. So again, really important to protect your reproductive organs. The ovum and female, again, same thing. Very radiosensitive. So ovaries, they do become radio resistant as females get older. That's kind of what menopause is. So, we shield our patients that are, from a certain age while they're still able to have children. So after menopause, of course, the ovaries are going to be less radio sensitive. But the thing is, as we get into more of the geriatric population, our cells become more radiosensitive again as we get older. So it's kind of like when you're younger, your cells are very radiosensitive. As you become an adult, they become more radio resistant. And then as you age into the geriatric population, then your cells can become more radiosensitive again. These I definitely would memorize for the exam or for your registry. Just note that it takes around 1.5 grays. You won't have to remember rads because grays will be on the registry for temporary sterility and permanent sterility of 5 grays. Okay, so you can see those are very high notes. And then for temporary sterility for males, it'll be around 2.5 grays and permanent will be 6. So females are a little bit more radiosensitive than the males. Okay. All right, so let's go over linear energy transfer and relative biologic effectiveness. This goes back, to what I talked about regarding measurements, weighting factors. So let's kind of cover these real quick because they are on the content specs. So LET is the rate at which energy is transferred to the tissue as radiation passes through. So we talked about absorbed dose being the amount of radiation that's absorbed by the body. Well, LET is the pathway that the x-rays flow. Once they're absorbed up in the tissue, those x-rays kind of go through this pathway to be absorbed by the body. So this is the rate of the energy. So we want to make sure that and the radiation that's entering and being absorbed by the body, if it's really, really strong radiation, of course it's going to do damage. It's going to have a really high LET. We take x-rays, like I said, all the time, and we can take x-rays without harming our patients, right? We can't shield. So when we take x-rays, we're able to get good images, and we do relatively low impact and harm to the patients. So that's why x-rays and gamma rays are considered low LET radiation, because they're not that harmful. So LET kind of is how much harm is it. Alpha particles, again, that'd be like a nuclear explosion. Beta and neutrons are considered high LET because they have high energy transfer. That's all that means. So high energy, high LET. Lower energy, like X-rays and gamma rays, low LET. Okay. I don't think you need to know how they're measured. Again, I don't think that's important. You might want to just know that diagnostic X-rays are around 3 LET, 3 keV micrometers. I don't think you need to know that though. I don't think I'd waste my time memorizing that. You got enough to remember. And then LET is useful in describing the quality of radiation as well. So again, low LET radiation are X-rays. High LET would be like alpha particles. So the reason why X-rays and gamma rays are considered low LET, it means that as the X-rays enter the body, most likely they're not going to cause direct harm to your patient. We do know that x-rays can be dangerous though, so they most likely, if x-rays do cause harm, they're going to cause them through this indirect action. And that's when they produce free radicals in the body. And free radicals essentially can interact with your DNA, and they could cause harm to your cells and kill some of your cells. They typically cause single-strand breaks in DNA. They don't break through the full DNA. So anytime you have radiation that can like cut through entirely and have a double-strand break in the DNA, it's going to kill that cell completely. And that's where, you know, if you have, for example, if you had skin burns, all of those skin cells are being destroyed due to that high LET radiation and those double-strand DNA breaks. All right. Like I said, alpha particles are going to be considered high LET radiation. These types of radiations are going to be really heavy, have a high mass and charge. I always say alpha, it's the easiest one for me to remember, but beta and neutrons are there as well. They're dense. So I always use this like analogy. Think of like these particles as like the sumo wrestlers. You know, they can do some damage if they hit the body. However, sumo wrestlers are not very fast, so if they don't, you know, they may not be able to, you know, they're only going to be able to hurt the body if they get a good hit. So the thing is that with this type of energy, it's really, really strong, but it's short lasting. X-rays can travel through the body really quickly, really fast, but not cause any damage. Alpha particles, like I said, they're really, really heavy. So they're going to cause a lot of damage, but they're only going to move a short amount of track in the body. So they're not going to travel very far in your body. But if they get ingested, if you were to swallow an alpha particle, if you were to breathe it in, if it was to get injected inside the body, it could essentially, you know, kill the tissues and cells. However, on the surface, an alpha particle, it honestly can't even breach the skin. So unless it's ingested, inhaled, injected, most likely we won't have any results from the radiation. However, you think about a nuclear explosion, you're going to inhale that radiation, you're going to ingest it, and that's how it's going to get in the body and do a lot of bad damage. I always think of like smoking cigarettes, right? You know, a little passing through a cloud of smoke's not bad, but if you're consistently ingesting and inhaling the smoke, it has the potential to do a lot of damage in the body. So double strand breaks, because it's so strong and heavy, is more essential with high LET radiation. So LET is directly related to RBE, right? RBE standing for Radiation Biologic Effects. So of course, as you have high LET radiation, such as alpha particles, you have the potential of having a huge radiation biologic effect, such as cell death. So RBE describes the relative effect. So really, it's just the capability of radiation to produce an effect or to produce harm, if you want to think of it that way. Biological damage produced by radiation increases as LET radiation increases. They have a direct effect. If you have a higher LET type of radiation, like alpha particles, you're going to have more biologic damage. So as LET goes up, so does RBE. They are the same. They are directly proportional. All right. It does talk about that you can kind of utilize an equation in the book. I'm going to skip over that. Well, okay. So the definition of RBE is the ratio of the dose from a reference test radiation to radiation produced by the same biologic reaction. So when we're using the reference radiation, they always use 250 kVp X-rays. So what we're doing is we're taking this unknown substance, right? This unknown type of radiation, and we're comparing it to 250 kVp X-rays, so a relatively low LET radiation. And we're seeing, is it high LET radiation or is it low, right? So in this particular example, it says a biologic reaction is produced by 2 gray of a test radiation, which means we don't know what type of radiation it is. So if there is 2 grays of this type of radiation and it takes 10 grays of X-rays to produce the same response, what's the RBE? Well, all you do is you take the the reference radiation, or you take the 250 kVp radiation, you divide it by the unknown or the test radiation. So we know we had 10 gray of 250 kVp, so you just take 10 divided by 2, which equates to an RBE of 5, right? So an RBE of 5 means that the test radiation is 5 times stronger than the X-rays. So if you think about the radiation weighting factors, X-rays have a radiation weighting factor of 1. Do you remember any types of radiation that had a radiation factor of 5? I believe there was slow neutrons. That had a radiation weighting factor of 5. So this unknown radiation kind of makes me think that this could be slow neutrons is what we're seeing here. And because it's 5 times stronger than X-rays. So that's just RBE. It's just, I don't think you'll have to do this mathematical equation, but I hope that makes sense. So again, the equation is just the standard or reference radiation, which is 250 kVp X-rays, over your test or unknown radiation. So again, as LET increases, when you have high LET radiation, you're going to have more biologic damage. It's directly proportional. RBE is the ability to produce damage, and of course, it's going to vary with LET. It just depends. So ionization may change a cell's molecular structure, thus affecting its ability to function properly. So of course, if you have ionized radiation hitting the body and it does damage, it's going to impair the function of certain cells. Radiation-induced damage is observed on the molecular level, the cellular level, and the organic level. So just remember that X-rays typically cause damage through an indirect effect by causing free radicals to be formed in the body. And it typically results in a single strand for DNA. So the cells typically with X-ray or low LET radiation can repair themselves. If it's high LET radiation, most likely the cell's going to die. So I want to mention too that somatic cell exposure, remember somatic means body, so somatic cell exposure may result in a disruption in the ability of the organism to function. Reproductive cells, which are obviously not in the body, they're in the fetus, exposure to that might result in changes called mutations being passed on to the next generation. And most radiation passes through the body with interaction because atoms are composed mainly of empty space. All right, so again, we talked about low LET radiation such as X-rays producing an indirect effect in the body by free radicals. We also have what's called the direct effect. So think about radiation striking a cell and hitting the cell and then essentially interacting with the master molecule and then killing the cell. So I like this example right down here. You can see here that in this example, this most likely is a high LET radiation because it was strong enough to breach through the cell and interact with the macromolecule. When we're talking about the macromolecule, most of the time it's talking about the DNA of the cell. So if the radiation is strong enough to interact with the DNA of the cell and produce a double-strand DNA break, it is going to produce a response that pretty much impairs the function of the cell to where it cannot repair itself. The cell will then die and you will lose, the cell will die, and the radiation will have caused that cell to die and it will not be able to repair itself. Now, the other type of radiation is indirect, and this is where radiation strikes not the DNA or the macromolecule of the cell, but it strikes the cytoplasm or water surrounding the cell. And that's where that indirect effect occurs. And that's where we have the formation of free radicals. That's what radiolysis or radiolysis describes when we're talking about the interaction of X-rays with water. And you can see in this example that it hit the cytoplasm or the water and nothing happened, which is, you think of x-rays, right? Like we take x-rays all day long. Yes, we produce x-rays, we shoot the patients, they have no harm. Well, you know, that's what the indirect effect is, because x-rays are low LET radiation. They don't interact with the DNA because they're not strong enough. However, you know, sometimes there could be an effect. So not a lot, but there could be an effect, and that's where maybe the cell won't necessarily die, but it could be impaired. Okay. All right, and all of this, what I'm describing, is what's called the target theory. So if an X-ray photon interacts with the macromolecule and kills the cell, that is the target theory. If it interacts with the cytoplasm or the water, because remember our bodies are like 80% water, you know, that's going to be an indirect effect. And you can, you can see here too that this gives the different pathways. So think this is specifically an X-ray photon, okay? And again, this is representing it's hitting the cytoplasm of the cell or a water molecule, because most likely it's going to interact with water. And it has a couple different ways it can go. So when it interacts with water, it does create ions. And when it creates ions have the potential to do damage. So if the ions end up interacting with the DNA macromolecule, then biologic damage could be produced. Or the ions could cause free radicals, and then biologic damage could also occur. However, most of the time, especially with x-rays, these ions actually just reform more water in the cell, and then nothing happens. And again, that's represented down here where nothing happened. So x-rays are not safe, you know, they're definitely not safe, but because they're low LET radiation, the amount of effects are going to go down, you know, tremendously. Okay? And direct effects really aren't going to happen with x-rays. Here's another great example where you have an x-ray photon interacting directly with the DNA and hitting the strand. And again, there could be a single strand break, but for that x-ray photon to break through the double helix and result in a double strand break, very, very not likely. The indirect action for X-ray photons is represented in this image here. When you have this, again, like I said, instead of interacting directly with the macromolecule or the DNA, it's going to interact with a water molecule instead. And this is where those ions are going to be formed, and free radicals could be produced, and then those free radicals could interact with the DNA and cause maybe a single strand break. This is the most common type of action when it comes to x-rays. Okay. The definition of direct action, biologic damage is occurring as a result of ionization of the atoms on the DNA, causing them to become inactive or functionally altered. Indirect action effects are produced by free radicals created by the interaction of radiation with water molecules, and they can also cause substantial disruption to the DNA and maybe result in cell death, but not typically likely unless there's large amounts of radiation. So cell survival and recovery, the lethal dose 50, this is good. This is could be on your registry. So cells that have been damaged by a sublethal dose of radiation can survive due to repair enzymes inherent by the biochemistry of the cell. So our cells are pretty, resilient. We do have repair enzymes that can mend our cells after radiation exposure. It just depends. So the combination of cells repairing themselves and repopulating cells that have been killed results in the recovery from the radiation damage. So again, the recovery from a lethal dose of radiation can occur. So let's kind of look at it. These are really interesting to me. It kind of gives us an idea of how radiosensitive our bodies are compared to animals that we commonly see. So again, if you don't remember, LD50 is the dose of radiation of the whole body that would kill 50% of the population or the exposed individuals. So we talked about numbers. This is specifically the LD5030. So this is the lethal dose that would kill 50% of the population within 30 days. And you can see it's an absorbed dose in grays. For human beings, it's going to be around 3 to 4 grays, right? So super, super high amount of radiation. It has to be like a full body dose. Again, the only thing I can think of is like a nuclear explosion where we get that high dose of radiation. But I want you to find it very interesting. Our fur babies, they're going to be about the same as us. If we're gone, they're going with us. But monkeys, if you have a pet monkey, it might outlive you. It has a LD5030 of 4 to 4.5 grays or 4.75 grays. Hamsters, they're pretty resilient. They can live, a lot longer than human beings. They're more radio resistant than we are. Hamsters, rabbits, rats, if you have any pet turtles or newts, they're going to be trying to survive. They're going to outlive us. So it'll take 15 to 30 grays to hit that lethal dose. So I find this very interesting. We're actually, in the species, we're very radiosensitive compared to other species in our world. LD5060 is the same as LD5030, except for it means that 50% of the exposed individuals would die in 60 days. So again, around a whole body dose of 3.5 grays would be the amount to kill 50% of the exposed individuals within 60 days, even 30 grays too. So I would use 3.5 gray, 3 to 4 is what our range is. All right, so let's go over a couple other things that are on the ART content specs: the oxygen effect, age, recovery, chemical agents, and hormesis. Go over those briefly. So the oxygen effect, again, like I said earlier, tissues that are high in oxygen are more sensitive to radiation. So it makes sense that if you have tissues that are more oxygenated, they're probably going to be damaged more by radiation. So we have what's called OER, or oxygen enhancement ratio. And this is the ratio of the dose required to produce a particular biologic response in a hypoxic environment to the dose required to cause the same response in an oxygenated environment. So remember, hypoxic means low or no oxygen, where oxygenated obviously is going to contain oxygen. So if you have a tissue that is low, if it's low in oxygen, it's going to be more radio resistant. So diagnostic x-rays have an OER of around 3. Okay, so in order to find that, you're going to do a simple equation where you put the dose required to cause a response without oxygen over the dose required to cause a response with oxygen. Not sure if that'll pop up in the registry, but it is in the content specs, I believe, so just review it if you can. Age, obviously, humans are radio sensitive when they are younger. They become more radio resistant, and then as we age, we become more radio sensitive again. So humans are more sensitive to radiation before birth, and it decreases as we mature. The elderly, again, become more radiosensitive. Cells can recover from sublethal radiation damage depending on how the cell can repair itself. If the dose is large enough to kill the cell before the next division, then interphase death will occur, and unfortunately, cell death and it cannot recover from the damage. So there is no repair after interphase death, okay? So intracellular repair and repopulation is what equals recovery. Also, different chemical agents can modify radiation response. So we have what are called radiosensitizers, and if you add these radiosensitizer chemicals to whatever you're imaging or whatever is being exposed to radiation, it will increase the effects of radiation. It's kind of like if you put on tanning oil and you burn, instead of putting on sunscreen, you use baby oil or tanning oil, you're probably going to burn more. So it has the same effect. It increases the effect of radiation. And then, of course, a radioprotector will decrease the effects of radiation. Oh, and the examples of radiosensitizers are halogenated I always mess up this word. Pyrimidines. These could be used in radiation therapy possibly to, if they're trying to kill a tumor. And then, of course, radioprotectors decrease the effects of radiation. An example of the chemical is cysteine. Again, I like to use the analogy. This one would be like putting on sunscreen, and this would be like putting on oil, right? You want to put on sunscreen to reduce the effects of radiation. The thing with radioprotectors is we don't typically use them because, unfortunately, it would take fatally toxic levels to protect us. So it's not like we could, inject cysteine into our bodies to help us become more radioresistant, because, if we injected that into our bodies, it would be toxic. Hormesis. I like hormesis. So, I don't know if you guys remember this, but hormesis is pretty interesting. It kind of goes back to those dose-response curves, and hormesis is basically a theory that presents radiation in the opposite way. We always think of radiation as harmful, where hormesis is a theory that radiation is helpful and it is healthy for our bodies to an extent, and some amount of radiation is actually can actually do the body good. So it is a possible beneficial effect of small amounts of radiation. This theory states that they could stimulate hormonal and immune responses and extend lifespan. And although this theory does exist in the medical field, we still practice ALARA. So we can't use hormesis as an excuse not to practice ALARA. Somatic effects. Remember, somatic effects are manifested in the exposed individual. Somatic means body. So when we're talking about short-term versus long-term somatic effects, it's obviously short or long-term effects to the body. Short-term is going to occur shortly after an exposure. I would say short-term is minutes, hours, maybe days. Long-term is going to be maybe, months, years. Weeks are going to probably be more short-term as well. So skin erythema or skin reddening and desquamation, which is skin peeling, those are all examples of short-term effects. And then biological effects that do not occur for years until after exposure are going to be long-term or late effects. So you have short-term effects and then long-term or late effects. All right, so this is extremely important. I would definitely make sure you review these charts. You should know which ones are short-term and which are long-term. So I want you to compare these two as well, because you will see terminology that's a little bit different. This is an older version of the text, and this is a newer version. So I want you to notice that they're in each box, it's the same box, but you'll see that this one's labeled early tissue reactions and this one's labeled deterministic effects. Deterministic means early or short term. So these should be used simultaneously. I don't know what verbiage you're going to get on the exam, so make sure you know both. But you can see nausea, fatigue, reddening of the skin, hair loss, intestinal disorders, fever, blood disorders, or shedding of the skin. Those are all going to be early tissue reactions or deterministic effects. Late tissue reactions or late deterministic. So these are not going to be long-term. These are just going to be late, maybe months or years down the road. Examples are cataracts that form in your eyes, fibrosis, organ atrophy, loss of parenchymal cells, reduced fertility and sterility. Now, when we talk about stochastic effects, those are long-term. Those are years down the road, at least, 5-10 years down the road. And the only two that are going to fall in that category are cancer and genetic effects. Okay. To go back to see how these effects are represented by those dose-response curves, again, this is that non-threshold linear effect. This is going to represent the stochastic effects. So genetic effects in cancer are represented by number 1. By 2 and 3, these are the threshold linear and the threshold nonlinear. The threshold nonlinear is going to represent all of those early effects and late tissue reactions, okay? So all of these, with the exception of the stochastic effects, are going to be represented by 2 and 3, 3 for the most part, And then cancer and genetic effects are going to be represented by this first one. All right, so again, when we're talking about somatic effects, because it happens straight to the body, it's going to be caused by high LET radiation. So this should say dose, I apologize. So it's a lot of radiation that is received by a large area of the body. It's going to cause that short-term effects. Doses causing these effects are much higher. So again, diagnostic x-ray, it's low dose, it's low LET, not high LET. And it's going to be somatic, again, means to the body, not to the genetic portion. So acute versus chronic, if you hear the terms, acute means sudden onset for a biological effect to occur, and it has to deal with a large amount of radiation exposure. ARS, or acute radiation syndrome, is an example of an acute effect. Chronic means over a time or prolonged. A chronic biological effect would occur later in life, and it would be result from low levels of exposure, such as cancer, leukemia, genetic effects again. So this is going to be that threshold nonlinear, and this is going to be that linear non-threshold dose-response curve. Reproductive organs, of course, are sensitive. Please make sure you know these numbers. So in both male and female, 2 grays of radiation can cause temporary sterility, and 5 gray can cause permanent sterility. Carcinogenesis, remember, that's cancer. It is the most important late stochastic effect caused by radiation. And it is random. So just because you have radiation exposure doesn't mean you're going to get radiation-induced cancer. It's random. And it doesn't have the threshold, so that's why we have to say non-threshold, because we really can't tell. Cancer can come up at any time, but it is a long-term effect. Cataracts of the eye, those are going to be a late effect, but they will have a threshold. So the probability means that there's usually going to be a high-dose radiation of about 2 gray that would cause the formation of cataracts. And fluoroscopy procedures cannot result in insignificant radiation expenditure of the lens of the eye from accumulative scatter radiation. So it's not likely that a fluoro procedure could cause cataracts, but interventional radiology, high levels of radiation on a daily basis with you not protecting your eyes could essentially cause cataracts, but it would have to be a lot. The skin, of course, is alive. Your skin is alive. You do have skin cells. So this is just stating that, your skin's important. So erythema or skin reddening and desquamation could result, or peeling of the skin from radiation. So when we talk about acute radiation syndrome, you should know the different syndromes. I definitely could see that coming up on the registry. So make sure you know that you have the Hematopoietic Syndrome, which is deals with your blood cells. So that's going to be where your blood cells are affected during this syndrome due to high doses of radiation. You have Gastrointestinal Syndrome, which is going to disrupt your GI tract, and then you're going to have your Central Nervous System Syndrome or your Cerebrovascular Syndrome, and that's going to be a complete failure of your nervous system. The Hemopoietic System includes bone marrow, circulating blood, lymph nodes, spleen, and your thymus. Of course, your lymphocytes and spermatogonia are the most radiosensitive cells in the body. So it's important, this is huge in terms of having, ARS or high level doses of radiation. The principal response of this system is a decrease in the number of types of blood cells in circulation. So if your blood's not working properly, of course your body can't work properly. So it occurs when people receive whole body doses of 1 to 10 gray. So I would maybe know that those doses. Your GI syndrome, of course, is the lining of your GI tract, and it divides very rapidly. It's considered radiosensitive. A large exposure could result in nausea, vomiting, diarrhea, and it appears at a threshold dose of around 6 gray. So again, we know that the LD5030 is around 3 to 4 gray. So, if you were exposed to up to 6 gray, you're going to have that acute radiation syndrome where you're going to see that you have GI syndrome probably before your body starts to shut down. Without medical support, exposed persons receiving 6 gray to 10 grays are going to die within 3 to 10 days. So a few hours after the dose required to cause a GI syndrome has been received, you will have some different phases. You're going to have the prodromal phase, which is the beginning stage where you start to feel nauseated, you vomit, you have diarrhea, and it's going to go on for about 24 hours. And then weirdly enough, you're going to have this latent period where you feel like you're okay, like everything's back to normal, everything's okay, and that can last around 5 days. And then after that, you're going to have the manifest stage, and that's where you're going to really start to get sick again, and you're going to start to go downhill. So the manifest stage is going to, cause more nausea, vomiting, diarrhea, and then of course your body's going to start breaking down. So some other signs and symptoms are for this GI syndrome could be fever, fatigue, loss of appetite, lethargy, anemia, leukopenia, hemorrhage, infection, and pretty much everything. That's not fun. So not good. So the Cerebrovascular Syndrome, or the CNS syndrome, the central nervous system and the cardiovascular system receive doses of 50 gray or more because they're the most resistant in the body, but they can cause death to within a few hours or 2 to 3 days after exposure. Again, prodromal or the early stages, you're going to start seeing signs such as confusion, nausea, vomiting, nervousness, diarrhea, loss of vision, burning sensation of the skin, loss of consciousness. And then, of course, a latent period that could last up to 12 hours is where all of those symptoms subside. You start feeling better. And, of course, the maniphase stage then happens after that, where everything comes back again, and it's increased and it's worse. And then you'll have all these other effects that you see here, which eventually would cause the person not surviving. So this is a nice chart that's from your shared textbook. You can see here that the prodromal phase is the initial phase. The latent is where you don't have any symptoms. And then all of these different dose amounts will result in the 3 types of stages here, and then all of the results here. So something good to review. Okay, so embryonic and fetal risks. Remember that the fetus is the most radiosensitive in the earliest stages of pregnancy. So the embryonic 2 to 8 weeks, the developing embryo is going to be sensitive at the beginning, first trimester. It's going to become less sensitive. So radiation of the embryo or fetus during the first 12 weeks of development to equivalent doses in excess of 200 millisieverts or 0.2 sieverts, could result in severe congenital abnormalities. That's why when we do radiation procedures that involve a lot of radiation, like lumbar spines, abdomen x-rays, CT scans, we really want to make sure the patient's not pregnant. And if they are, the sooner they're pregnant, the better. The sooner they are in their pregnancy, the worse it is to image them because of the first 12 weeks being so vital. So death of the embryo or congenital abnormalities could happen along with all of these other effects if that fetus is exposed to radiation. And that's why it's so important that we do not image pregnant patients ever. So genetic impact, hereditary effects, they do not have a threshold dose because this means that even the small amount of radiation dose could cause a hereditary damage. Again, going back to that linear non-threshold dose response curve, cancer and genetic effects follow under that category. So make sure you're always protecting your patient's gonads. Okay. Lastly, genetic significant dose, or GSD, is the estimated gonadal dose received by the population. And although the dose from the gonadal dose from diagnostic x-rays is low for each person, it could have an effect on future generations in terms of mutations. Remember, Our knowledge with radiation is only about 100 years old, so it's still relatively new. That's why we're so conservative when we deal with radiation, because we're still learning about it. So all of these increases in technology and radiation, you know, we don't know how this radiation exposure is going to impact our generations in the way future. So the more information we get about radiation, the more prepared we can be. But that's why we should always play conservative and really follow ALARA whenever we can. So to prevent mutations in future generations, of course, we want to make sure that we're using low radiation doses and we're reducing the amount of radiation exposure to the patients whenever possible. Okay. Gonadal shielding, this has been in the media lately, kind of interesting, but the effect is dependent on the rate at which the radiation is delivered, protraction, and the time in between exposures or fractionation. Females are less sensitive to the genetic effects of radiations than the male. That's because the male's gonadal area is more exterior, whereas the woman's gonadal region is protected by the abdomen. And most radiation-induced mutations are recessive. Okay, so the frequency of radiation-induced genetic mutations is low. So we've only been able to see that there are about, I think that's 10 to 7 mutations per rad per gene. So it's relatively low. You don't have to memorize that. But radiation-induced genetic mutations follow the levels of exposure experienced in diagnostic medicine are low, and the probability is rare. So it's good that we're practicing ALARA, and we should continue doing so. And that is my last slide. So I went through this relatively quickly, so please feel free to review it and reach out to me if you have any questions, okay? Thank you, everybody.